Okay, so today we are going to be talking about phase changes, and I know most of you had dealt with this earlier when you took chemistry, and probably have dealt with phase changes all the way through elementary school, all the way through junior high school, and like I said, in chemistry, and now you're going to be dealing with phase changes again in physics. So we're going to be talking about the phase changes. Well, we know right away that there's 3 states of matter, and actually there's more than 3 states of matter, but in this class we're going to study the 3 main states of matter: a solid, liquid, and a gas. So everything that we're going to be dealing with is going to be solid, liquid, and a gas. And what we normally like to talk about is water, the 3 states of water. The solid is an ice cube, the liquid is a glass of water, and the gas is steam. So we're going to be talking about those 3 and how they interact and how they change from one form to another. So the phase changes are really going from a solid to a liquid to a gas, or a gas to a liquid back to a solid. So this happens routinely, and it follows a chart right here. Well, the one way to get a phase change is heat has to be added. And that only makes sense. If you're going to try to boil water and it's going to turn into steam, you have to turn the stove on. So you're going to be adding heat to the water to create the phase change. But now we're going to talk in more detail about the physics behind it. So here I have a chart, and on my y-axis is the temperature, and we're going to be talking about the temperature in degrees Celsius, and then we're going to be talking about the heat that's going to be added. So we're going to start here at 0 heat added, then we're going to turn the stove on, and heat is going to be added more and more to this substance, and in this case it's going to be water. So if I stick an ice cube, a bunch of ice, in something on a stove, right away, this area right here, it's solid ice. It's not going to start melting, it's just a chunk of ice. And heat is going to be added. So I turn the stove on, and we're going to be adding heat in the terms of joules, which is our Q. And we're going to add heat, and as we add heat, the only thing that's going to be doing is the temperature of the substance is going to be increasing. So we're going to go from negative 25 degrees all the way to 0 degrees. And you can see here, but all you still have is pure ice. There's no water involved. So every bit of heat that's going to be added, the 61.7 joules, is going to be absorbed in changing the temperature from negative 25 to 0. Once we hit 0 degrees Celsius, and we know that that's the freezing point, okay, or the melting point. So at this point, all of a sudden the ice starts to melt and become water. But the temperature doesn't change. The temperature here is going to stay at 0. In this phase right here, this is where our phase change occurs. All the heat that's added, the extra heat from 395.7 to 61.7, is all absorbed in melting the ice. Okay, then what happens, and we call this right here, this is our melting point. Okay, and that number is pretty familiar to most people, that ice melts at 0 degrees Celsius. Or we could say that it's also the freezing point. Then what happens is there's no more ice left. Your pure water at this point, 395.7 joules. The temperature now starts increasing, so all this extra heat that's going to be added from here to here is going to be used to increase the temperature from 0 to 100 degrees. At 100 degrees, and you should be familiar with that, 100 degrees is our boiling point. So once we reach 100 degrees, what happens is now we stay at a plateau. The temperature doesn't change, and so all the heat, or all the energy that's going to be added, is going to be added to go through a phase change of water and steam. And this mark right here just signifies that it's a longer time period, and longer heat is more heat is being absorbed into the water than we have room on our chart. Okay, so you can see here to 3,073 joules, 813 joules. So now the temperature stays constant, and then at this point now there's no more water. It's 100% steam, and then the heat is still being added, and then we're going to increase our temperature. And we're not really interested in what happens after here. So what we can say is, as the temperature increases from negative 25 to 0, the ice has not even started to melt. But as the temperature hits 0 degrees, we've hit our melting point, and the melting starts to occur. during this phase change, there's no increase in temperature right here, and all the energy is absorbed to change from ice to water. Then we have the same thing happening here. Once all the ice is melted, the energy is now being used to raise the temperature from 0 to 100 degrees right along here. And once we hit 100 degrees, 100% of the energy is being absorbed into the phase change. And that's what's going on here. And we're going to look at this, we're going to do a lab later on that we are going to create a phase change chart just like this, but not with water, with a different substance. Okay, so now we're going to go into something that's called latent heat. And latent heat is just going to be the energy of the mass that is transferred during a phase change. So yesterday we talked about the equation that Q, the MCAT, this is the energy during a temperature change. But we just talked about back in this chart right here, when there is no temperature change, what is this Q value? So the MCAT equation is used here and here and here when there's an increase in temperature, but how do we find the Q that happens during these areas here? Well, those are latent heat phases. Okay, so the latent heat, and we use H. Some books, they use, an L instead, but in our textbook we use the capital letter H, latent heat. It's the energy per unit mass that is transferred during a phase change. Okay, the equation that we use here is Q equals mH. M is the mass of what is being melted or boiled, and H is going to be a constant. That's our constant, the latent heat. There's two types of latent heat. There's latent heat of fusion, which is sub F, and latent heat of vaporization, that is sub V. So this is used when we go from a solid to a liquid, or a liquid back down to a solid. And this is when we have a liquid to a gas, or a gas to a liquid. So if I bring this chart back up again, we're going to have latent fusion during this point and latent vaporization during this point. Okay, now these equations, these constants are available on page 324 of your textbook. It's table 12.2. Okay, so these are just constants that are going to be given to you, and they are figured out in a lab. Okay, so we can know that we're going to use latent heat of fusion to fuse something together, solid to a liquid, and vaporization. When you have vapor, you have gas, so it's liquid to a gas. So let's try an example. Okay, so the first one that we're going to be working on is how much heat is needed to melt 5 kilograms of ice at 0 degrees Celsius and then heat it to 95 degrees Celsius. So the first thing that we have is we have a temperature change from 0 to 95, but we also see how much heat is needed to melt ice to water. Okay, so we're going to have both situations going on here. We're going to have an ice cube, it's going to melt to water, and then the water is going to be raised in temperature here. So from this phase, from the ice to the water, we're going to have the heat added is going to be the latent heat of fusion. And then from the water to a raised temperature, it's going to be your MCAT equation. So the total heat is going to be this one plus this one. So let's solve this. How much heat is needed to melt 5 kilograms of ice? So we have the mass is 5 kilograms of ice. The original temperature is 0 degrees, and then heat it to 95. We have the final is 95 degrees. The specific heat is 4180 joules per kilogram degree Celsius or Kelvin. We can use either one. And then these two come from the table in our textbook. So we have the latent heat of fusion is 3.34 times 10 to the 5th. The latent heat of vaporization, 2.26 times 10 to the 5th. Now we know we're only going to be dealing with fusion because we're only having the ice is melting. So we're not even going to use this equation. So what we want to do is we have two steps. We're going to be looking at this. This is going to be our step 1. So if I want to know the Q to melt the ice to water, it's going to be mL Well, the mass is 5 kilograms. And the latent heat of fusion right here, I shouldn't say this is HF. I learned LF, so I'm gonna probably make a lot of those mistakes, but that's HF is 3.34 times 10 to the 5th joules per Kelvin, degree Kelvin. So if we multiply those two together, we have 1.65 times 10 to the 6th joules. Oops, I'm sorry, this is joules per kilogram. Okay, so this is how much heat is needed to be added to melt that ice. Now we have to look at the second phase, right here. And this is when the temperature is going to be raised from 0 degrees to 95. So we're going to say Q2, the heat added for this part, is your MCAT equation. Okay, the mass hasn't changed, it's 5 kilograms. Now we have our specific heat of water, which is 4180 joules per kilogram degrees Celsius. And our change in temperature, our final temperature is 95. And our original temperature is 0 degrees. Okay, so if we multiply that all together, we end up with 1.99 times 10 to the 6th joules. So this is how much heat is needed to raise the temperature from 0 to 95 degrees. Now the question is asking how much heat is needed to do both. Well, our total Q is just going to be Q1 plus Q2. So we can have 1.65 times 10 to the 6 joules plus 1.99 times 10 to the 6 joules. So the total is 3,635, 500 joules. So that is your total answer. Okay, so the big thing here that you want to remember is that we have latent heat of fusion when we're doing a phase change during that constant temperature, and then we have your MCAT equation whenever there's going to be a raised in temperature. So we can have one or the other, or in this case, a combination of both. Don't forget to do your assignment, and we'll see you tomorrow in class.